Alright, this is a tutorial on identifying a rate law based on initial rates. Here we're given a set of data. This data shows concentration versus initial rate. We have 3 experiments here, 1, 2, and 3. These were all carried out with different concentrations of reactants, and they were designed to detect the initial rate given those concentrations. So our goal is to find the rate law. Remember that a rate law tells us the rate of the reaction with respect to the rate constant times the concentration of one reactant, here we'll use fluorine, to some component X, times the concentration of a second reactant, ClO2, to its exponent Y. We're going to have 3 goals here. We're going to have a goal to define what the first component X is, what the second component Y is, and then we're going to try and find out what the rate constant is. Alright, so how do we do that? If we want to find out what X is with respect to F2, we need to find 2 experiments where the concentration of F changes, but the concentration of ClO2 does not change. We need to isolate just the F2 changing. So if I want to do this, I'm going to want to compare experiment 1 with experiment 3. Going from experiment 1 to 3, F2 concentration doubles, and the ClO2 concentration does not change at all. Alright, so for this first one, I'm going to compare experiment 1 and 3. So I'm going to put the rate of 3 over the rate of 1 is equal to the concentration of F2 from experiment 3 over the concentration of F2 from experiment 1, and we're going to see what power this needs to be raised to get that equality. Alright, I like to put the larger numbers on top so that I don't have to work with fractions. You could have just as easily put rate 1 over rate 3 equals concentration 1 over concentration 3 to the power of x. But then you would have to deal with decimals. Here, when we do it this way, our rate 3 is 2.10 to the negative 3 molarity per second. Our rate 1 is 1.2 times 10 to the negative 3 molarity per second. Our concentration 3 is 0.20 molar. Concentration 1, 0.10 molar. Again, I got all this information from up here and from over here. Alright, this equality, as we plug this into our calculator, we see that this is 2 equals 2 to the x, therefore x equals 1. So this is first order for the concentration of fluorine, meaning a doubling of the fluorine caused a doubling in the initial rate. Now we'll do the same thing to investigate ClO2. Alright, so I'm going to erase these comparisons. We're going to figure out new comparisons to do. If we want to investigate the ClO2 to figure out what Y is, we need to isolate ClO2. When does ClO2 change and the F2 stays the same? Right here we see the F2 is going to stay the same between experiment 1 and 2, and the ClO2 is changing from experiment 1 to 2. So we're going to compare rate 2 over rate 1 to isolate this ClO2 change. Now we're finding the exponent y. So if we can find this equality, we can identify what y is. So we put the rate of 2 over the rate of 1. We set that equal to the concentration change of experiment 2 for ClO2 to experiment 1. And we solve for y. And here that we can see once again, now we're going to get 4 equals 4 to the y. Once again, we have a situation where we are first order. our exponent is a 1. Alright, so we have first order with respect to x. We have first order with respect to F2, which is our x. First order with respect to ClO2, which is our y. And so overall, this reaction is second order overall. So let's take this x and finish out our rate law. This is going to be mistake there. It's second order overall, but this is a 1. And this is a 1. So overall, we're second order, but we're first order with respect to each component. Alright, now we'd like to find out this K value. We found the order of the reaction. We need to find the K value because that'll finish off our rate law. In order to find the K value, we can take any of these experimental data sets and plug them in and solve for the rate constant. Experiment 3, Experiment 2, or Experiment 1, if we plug in the right values and pay attention to our exponents and our units, we should get the same K each time. So I'm going to pick experimental data set 3. Alright, the initial rate for experimental data set 3 is 2.4 times 10 to the negative third molarity per second. So that's going to be equal to K times the concentration of F2 to the power of 1 times ClO2's concentration in experiment 3 also to the power of 1. Raising things to the power of 1 is easy. That's just the 0.2 molar and the 0.01 molar. So I divide that into 2.4 times 10 to the negative 3. And I find that this K is equal to 1.2. Now you might be curious, well, what are the units? These are molarity units on this side. When I divide them over onto this side, the first one will cancel this top molarity unit. But because the reaction order is second order overall, I'm going to get a molarity unit in the denominator. The second molarity unit ends up staying in the denominator over here. So K is going to be equal to 1.2 with the units of 1 over molarity seconds. Again, you should have been able to plug in experiment 1's data set and experiment 2's data set and gotten the same relationship. So there's the rate law.